Okay, let's go then. Let's start with experiments. What is an experiment? An experiment is a process by which observations are generated. So I'd like to start with the most simple experiment that I can think of, and that is to toss a fair die once. Toss a fair die once. So obviously when you toss a die, the thing with the 6 sides, right? There are 6 outcomes. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 is my sample space. So the sample space is denoted by the letter capital S or the letter capital U for universal set. So your first homework is going to ask you, what is the universal set? What is U? Right? So just circle this thing so that S and U are used interchangeably. So my sample space S is the set of all possible outcomes. 1, 2, 3, 4, 5, and 6 are my outcomes, and there are 6 of them, obviously. And this is a finite and discrete sample space. I want to explain what I mean by that. It's finite because there are only 6 of them. So finite as opposed to infinite, which means it just goes on and on and on and on. And it's discrete. And by discrete, I mean it's not continuous. So any space that's discrete looks like this. Meaning it has little masses of probability with nothing in the middle. So here's a 1 with probability 1/6, and a 2 with probability 1/6, and then lastly I have a 6 with probability 1/6. And there's nothing in the middle, meaning no probability here. Just the opposite of something that's not discrete is called continuous. So something like this is a continuous sample space between 2 and 5, like this. X such that 2 less than or equal to x less than or equal to 5. This means the whole set from 2 to 5. You get it? This is continuous. This is a continuous line interval between 2 and 5. So this space is continuous and it's infinite, because there are an infinite number of possibilities in here, including 2.99684, like that. And every time you think you've counted them all, you can always take the average of one and the first point and get another point in the middle, like this. Take the average of this and this, you will get a point in the middle. Take the average of this and this, you'll get a point in the middle. Like this and this, you get a point in the middle, like that. And this can go on for the rest of your life, ad infinitum. So it's infinite. This is also infinite. It's just excluding the endpoints like that. This is an open interval 2, 5. This is a closed interval 2, 5. Are you with me? So these are continuous infinite sample spaces. This one's not. This one's finite, 1 through 6. And discrete. It's not a continuous line interval. So, number of eggs in a robin's nest. What do you think? Finite and discrete or continuous? Right, discrete, because you can have 0 or 1 or 2 or 3 eggs in a robin's nest, right? How about the temperature of the turkey on Thanksgiving Day? It can be 300 degrees, it can be 300.0126 degrees, and so forth. So that would be a line interval between 300 and 400. You get it? That would be continuous. So temperature, pressure, volume, things like that are continuous. Things that you count, obviously, discrete. How about shoe sizes? 5.5, 6, 6.5, 7, 7.5 wide. Discrete, finite or infinite? Finite. Okay, I think you have it. Any questions on what we just did? Let's define an event in this sample space. So what is an event? Look over here. It says an event E is a subset of the sample space. It provides the collection of outcomes that correspond to some classification. So for my experiment, I would like to define E1 as the event that a prime number occurs on the die when it is tossed. So what are your prime numbers? Don't say 1, don't say 1. 1 is not prime, right? The first prime number is 2, and then I have 3, and then I have 5. What is a prime number? Its only factors are itself and 1, right? So 2, 3, and 5 are the prime numbers, so I list them here. E1 equals 2, 3, 5. And then I use the classical probability concept, which I see on page 4. Can you go to page 4 right now of the typed notes, please? I'm here. If there are n equally likely possibilities of which one must occur, and S are regarded as successes, then the probability of success is S over n. So look at my stuff here. Look at my E1. I have 3 outcomes which are regarded as successes. 2, 3, and 5. So I go like this. 1, 2, 3 outcomes. S is 3 for this example, and n, of course, is 6. So the probability of E1 is given by 3 out of 6, which is 1/2. Because there are 3 outcomes that fit the bill. There are 3 prime numbers. That's what I'm trying to say. Similarly, if I define E2 as the event that an odd number occurs on the die, then 1, 3, and 5, again, I have 3 of them. So using the classical probability concept, S over n would again be 3 over 6 or 1/2. Are you with me? Okay. Any question on this page at all? Okay, it's making me crazy. Doran. Okay, thank you. Doran. And then it's like a Persian last name or something, right? Just tell me, because I can't concentrate on what I'm doing. Puladi. I got it. Okay. Thanks. I'm moving on. Do you have questions? Any question on page 1? Let's go to page 2. Thanks, you put me out of my misery. Now I can concentrate on what I'm doing. So I'd like to talk about union and intersection. Easy stuff for you guys, I'm sure, right? Have you seen this before, Venn diagrams? Yeah? Okay, so first thing I want to define is the intersection of set A and set B. Something like this is called a Venn diagram. It allows me to show my sets. I have 2 sets here, 2 events here, E1 and E2. So a Venn diagram just allows me to display my sets so that I can see the union and the intersection. Let me talk about this first picture right here. The green stuff that you see is A and B, A intersection B, which is A and B. That means that everybody in the center here belongs to set A as well as to set B. So if I was talking about E1 and E2 as we define them, where E1 is made up of the primes and E2 is made up of the odd numbers, then the ones that are common to both are 3 and 5, and therefore the 3 and the 5 would go into the intersection of these two sets, meaning they belong to this circle and they belong to this circle. Then I look at this set and I say, well, E1 is 2, 3, and 5, so 3 and 5 are taken care of, but 2 is not. So 2 goes here in E1, but outside of the E2 circle. And 1 goes in E2 and outside of the E1 circle. And then the outcomes 4 and 6 are nowhere in either of these circles, and therefore they are outside, in the space outside, but still within the sample space S. Are you with me? So in any Venn diagram, there are 4 areas that you should know right off the top of your head. By the way, there's no cheat sheet for exam 1, but there will be a cheat sheet for exam 2 and the final. So for exam 1, you're going to memorize everything. That allows me to keep the questions simple for you, because you're not referring to a formula sheet. If you were, they would be much more complicated. So memorize this, just understand it. I have 2 circles here, A and B. We've already talked about A intersect B, where intersection is shown by an upside down U or an upside down V. So A and B is denoted this way, and A and B is this area. So I want to talk about the other areas. This area right here, this area, puts you in A, but outside of B. So when you are here, you are in the A circle, but outside the B circle. So this is denoted A and not B, where not B is shown by a line above the B. A not B. A and not B is the same as A not B. This one is B not A. So this is a B circle. So this is B and not A. Meaning you are in B, but outside of the A circle when you are here. And then let me create a sample space here. This area right here would be not A and not B, because you belong to neither when you are out here. And this one, of course, is A and B. And these 4 are shown on your class notes right here. Get it? Any question? Okay, let's talk about this not. Not B, not B, not B. 3 different ways of saying not B. So I can say B bar, B prime, B complement. Complement, not like complimenting someone, but C-O-M-P-L-E-M-E-N-T. Complement. That means outside of B. So if this is B, this is outside of B. B, outside of B, but within the sample space S. So B and not B are mutually exclusive sets. What I mean by that is they're non-intersecting. You see this? A and B? A and B are mutually exclusive. That means that there's no intersection. So these also have no intersection. B and not B are mutually exclusive. Agreed? Okay, so I'm going to write a formula. Probability of B plus probability of not B equals the probability of the sample space. Do you agree with that? Probability of the sample space is 100% or 1. Therefore, the probability of not B is always 1 minus the probability of B. All I did was bring this to the right-hand side. So we use this already in our everyday lives. If the probability of snow is 10%, then the probability of no snow is 90%. 1 minus 10, which is 90. Get it? Okay. So let's see what's happening here. Oh, look, I'm using the classical probability concept. I just want to point that out here. It says the probability of E1 and E2. I see that E1 and E2 have 2 items in it, and therefore the probability of E1 and E2 would be 2 out of 6 or 1/3. That's just my classical probability concept going on here. And guess what? The probability of not E1 and not E2 would also be 2 out of 6 or 1/3. What would be the probability of not E1? The probability of not E1. Yes. 3 out of 6. These 3, right? This, and this, because I want to be outside the E1 circle. That's all. Let's move on. There's something called the union formula, which provides for me the probability of the union of A and B. So there are 2 ways to look at the union. And you're probably saying, what is the union? She never defined it. She's going to define it right now. Look, here's A, here's B. The union of A and B is made up of anybody that's in A or B or both. So all of this space is the union. You can be in A and you will be in the union. You can be in B and you would be in the union, or you can be in both and you would be in the union. So it's not like our English language, where if I said to you, your exam will be Tuesday or Thursday, that means it's either going to be on Tuesday or it's going to be on Thursday and not on Tuesday. But in mathematics, in probability, that's not the case. Probability of T or TH, Tuesday or Thursday, means it could happen on Tuesday, it could happen on Thursday, and maybe it could happen on both of those days too. So that's a difference, and you need to make a note of that in your own mind. Okay, so there is something called the union formula. Let's again call this A and B. I have 2 options when somebody asks me for the union. I can add up 3 mutually exclusive pieces like this, plus this, plus this. I'm making up these numbers. So I could add up these 3 pieces that don't intersect. The first piece is this one right here, this one, that piece, plus this piece, plus this piece. And since they don't intersect, I don't have to worry about removing anything, or I don't have to worry at all. Just add 3 mutually exclusive pieces to get the union. I could do that. So the union of A and B would be 0.1 plus 0.2 plus 0.3, which is 0.6. I could do that. Or I could use the union formula, which says take all of A, add it to all of B, and then clearly this portion was already included in A, so you don't have the right to add it again because it's overkill, so you're removing it one time. Watch my fingers. You take A and you add it to B. So you see this whole middle portion was already included, this piece was already included in A. So if you try to include it again in B, all this crosshatch portion is too much probability included. So you're going to peel off the middle portion so that you're left with all of A, all of B minus this intersection part, because you already added it the first time around, so you're adding it twice now. So take it away one time. So the question is, which union formula will you use? The answer is you use whatever is most convenient. If they give you A and B and the intersection, you would use that formula, probability of A plus probability of B minus the probability of A and B. This is equal to the probability of A union B. I would use this one because they gave me this and this and this. On the other hand, if they give you a Venn diagram with everything all marked up like this, you wouldn't bother with A and B and A and B, because in order to find A, you would have to add this and this. And in order to find B, you would have to add this and this, and then go and subtract this. So why bother doing all that when they're already all separated for you? They're mutually exclusive. Follow me? Okay. What's your question? It's clear? I'm moving on then. If you think of something, just yell out. So here I wrote them as the three pieces that they really are. A and not B, that's this piece. Plus A and B, that's this piece. Plus B and not A, that's this piece. Three mutually exclusive pieces being added together. Any question? Okay, next page. Page 3. Oops, sorry, excuse me, 1 second. There's too much paper. There are three ways to say mutually exclusive. The two other ways are incompatible and disjoint. So compatible means intersecting. These are compatible. These are incompatible. These are disjoint, mutually exclusive. These are compatible. So when two events are incompatible, their probability is 0 because there's no intersection. In that case, the union formula, which used to be this, A union B equals all of A plus all of B minus A and B, that union formula boils down to just probability of A plus probability of B, because this third piece, A and B, is 0 in the case where they are mutually exclusive, because there is no intersection. Follow me? And then this one is just an extension of the one above it, because here there are 4 mutually exclusive events, A, B, C, and D. So this same rule, probability A plus probability B, applies to all 4 of them. They don't intersect. This is A, this is B, this is C, this is D. They form a partition of the sample space S. So what is a partition? A partition of the sample space S means that not only do they not intersect with one another, but the union of them is the sample space S itself. And so you can see here that this space S is being partitioned by A, B, C, and D. They do not intersect, and their union is all of S. So take an example. The evens and the odds partition the sample space 1 through 6. Right? They are mutually exclusive, and the union of them is S itself. You get it, right? So this is just an extension of that. Next page. So there are 3 rules. The first rule is that the probability of any event A is a number between 0 and 1, meaning there's no such thing as 200% chance of rain. It doesn't make sense. The probability of rain can at most be 100%, which is 1. Probability of any event can be maximum 1. And you cannot have negative probability to the left of 0. So 0 less than or equal to probability A less than or equal to 1. The probability of any event is non-negative, and the maximum is 100%. The second rule is that the probability of this whole sample space S is 1, or 100%. And the third rule is if you have a bunch of disjoint, otherwise known as mutually exclusive events, then the union of them is just the sum. This is not new. We saw this on the previous page. It's the same rule here. Probability of A union B equals probability of A plus probability of B. If I added a union C here, I would add a plus probability of C here. Oh, you can't see what I'm doing. I'm saying that we already saw this rule on the previous page. So now I'm just adding one more event, probability of C, and adding A union B union C to this. And that's this rule right here. A union B union C equals the sum of all the probabilities. So you just take this, and that's the union. Follow me? So for 3 disjoint events, you can just go add them. But these are compatible events. I still have 3 events, A, B, and C. But these are compatible, these are not. So in the case of compatible events, I have to be really careful the same way I had to be when there were 2 of them. What did I do when there were 2 of them? Let's back up for a minute. We said, let's take all of A, let's add it to all of B, and then I have to take away the intersection because the intersection was already included in A, correct? Now I have this situation. So how about I take all of A, add it to all of B, clearly there's intersection, add it to all of C, now there's definitely overkill here. So let's go and take away all the intersections 2 at a time. So you take away A and B, and you take away A and C, and you take away B and C, and now you've taken too much away. So you go back and you add the middle portion in again. And that's what this formula says. You don't have to memorize it, just kind of understand what's going on. I added all the circles, then I removed the intersections 2 at a time. I had removed too much by removing this. I go back and I add the middle portion in again. However, if the little pieces, if the little mutually exclusive pieces are shown like this, 0.1, 0.2, 0.3, 0.1, 0.05, 0.05, 0.04. How do you find the union? Pardon me? Yeah, just add all the little mutually exclusive pieces the same way I was doing here. Wasn't I doing this and this and this before when I only had 2 circles? My one option was to add the 3 mutually exclusive pieces up and not bother with this plus this minus that. right? And I can do the same thing for the three of them. I can say, well, this piece doesn't intersect with this piece, doesn't intersect with that, or that, or that, or that, or that. So just go add them all up. And that would give you the probability of the union. Follow me? Any question? And how would I find this probability? 1 minus, exactly. 1 minus the probability of the union. Next page. How's the pace? Does the pace work for you? Just let me know if it's too slow, too fast. I can adjust. Next page. So the next page talks about the frequency interpretation of probability. So let's go back to page 4 in the typed notes. And I'm here in the second paragraph. The probability of an event E is the proportion of times the event occurs during a long run of repeated experiments. So let's say that I have a coin and I want to determine if it is a fair coin. So I toss it repeatedly. I toss it 1,000 times, and I see that it only turns up heads 280 times. So from this statement, I deduce that the probability of heads is 280 divided by the total number of tosses, which was 1,000. So my rough idea of the probability of heads for this coin is 0.28. It's a rough estimate. It doesn't mean that it's exactly 0.28, but it'll be somewhere in that realm. We'll talk about proportions and hypothesis testing regarding proportions later in the semester. Anyway, I'm going to conclude that this is an unfair coin. I have used the frequency interpretation of probability, which says if you do something repeatedly, the probability of an event E is the proportion of times the particular event occurs. So I'm repeatedly tossing the coin, and it showed up heads 280 times, so there's no way I can conclude that this is a fair coin. Follow me? Okay. The next set of green stuff is talking about De Morgan's law. So De Morgan had two laws. The first law says that A union B not. Remember that there are three ways of saying not. You can say C prime, C bar, or C, this is a bad choice of letter. Let's make it Q. Q prime, Q bar, or QC for complement, right? This is the one I'm using. A union B not. Sorry, this would be that one. This would be this one. And I could also say A union B C for A union B not. And all of them refer to this space. This is A union B, and I'm talking about this space here, A union B not. So De Morgan came along and said that A union B not, meaning this space outside of A union B, is equal to not A intersect not B. All I've done is taken this negation, this negative sign, this not, and distribute it to each value in the parentheses. So this A becomes not A. This union becomes intersection, not union. I just turn it around, and then not B. And I want to show that this is true by shading as well as by Venn diagram. So here I'll draw a Venn diagram. Here I'll shade this, and I want to show that this intersection is the same. So watch me. Here's A union B. Here's A union B not. And I want to show it's equal to not A's intersection with not B. So I'll go over here. Not A. Not A is shaded horizontally. Everything outside of A. Notice that I don't care if B is in it or not. I just took my A circle, this circle right here, and I shaded everything outside of this A circle, and that is not A. Agreed? Oh my. Thanks. So I took the A circle, and I shaded everything outside of the A circle using horizontal lines. And next I take the B circle, which is this. This is my B. And I will shade vertically everything that's outside of B. So here's outside of B. And I'm shading it vertically. And I want to show that the intersection, that means both things have to happen, the horizontal shading as well as the vertical shading. And I want to show that where both things happen is exactly the same as this space, the stuff that's outside of A union B, because this is A union B. And everything outside of A union B is here. So I want to show that these two are the same. I think that's pretty obvious, right? That's the first of De Morgan's laws. The second of De Morgan's laws is the other one that goes like this. A and B naught is equal to A naught union B naught. So let's shade that one. I also want to do a truth table for this in a minute. So A and B, here's A and B. This is A and B right here. And A and B naught is everything that's outside of this space. So this is A and B naught. Everything outside of the checked area. That's A and B naught. And I want to show that that's equal to not A's union with not B. So I already did that, right? I did show not A with horizontal lines, and I showed not B, which is everything outside of the B circle, with vertical lines. And this time I'm interested in the union of the horizontal and the vertical. So remember what union means. Union means include it if it's in the first set, or the second set, or both sets. That's what union means, right? So here, this means include horizontally shaded items and vertically shaded items, and both. The only one that's not included is this. Same area as all of this shading, because the only thing that's not included is this. So by shading, you can show De Morgan's law, each of them. And then you can also do a truth table. Do you remember your truth tables from 10th grade or 9th grade or something like that? Yeah? I'm going to show you. So let's start with one of the laws. Let's see which one I did here. It looks like I'm trying to show that P or Q naught is equal to not P and not Q. Let's start from scratch, because this is annoying when someone just keeps pointing to stuff. So, first of all, when I have two events P and Q, you can call it A and B, P and Q, it doesn't matter. When you have two events P and Q, for every value of P, Q could be true or false. So first of all, P can be true or false, and then for each value of P, Q can be true or false. So in all, I have 4 different scenarios. One scenario is that both of them are true. That's here, true and true. The next scenario is that the first one is true, but the second one is false. The third scenario is that the first one is false and the second one is true. And the fourth one is that they're both false. And that's where these come from. I don't know if you remember, but I remember when my teacher taught it to me, they would say, just write what I'm writing. P, true, true, false, false. Q, true, false, true, false. And I just memorized it, and nobody ever explained, why are you doing what you're doing? So if you just draw a tree diagram, it makes it pretty obvious that these are the only 4 scenarios that could ever happen if you have 2 events, P and Q, right? As you can see from the tree diagram. Are you following me, or am I losing you? Okay, so these 4 scenarios are these 4, and for every scenario, every one of these scenarios, I want to show that De Morgan's law holds. And I'm going to pick one of the laws. And it looks like the law that I picked here is A union B not. You see this squiggly thing, this tilde thing? This is the same as a negation. So when you're talking about truth tables, a not is written like this. When you're talking about probability, a not is written like this. A not, A not, A not. But they mean the same thing. They all mean nots, right? They're all nots, negations. So I'm here, and I'm trying to show that P or Q not is equal to not P and not Q. And I want to show that this column, not P or Q, is equivalent to not P and not Q for every scenario. And once I do that, I would have showed this law, De Morgan's law. Follow me? Yeah? Am I losing anybody, or it's just very simple for you? Clue me in. You've seen this. It was on your regions. Right? 9th grade or 10th grade, depending on if you were accelerated or not. So, without looking, can you do it? And then let's talk. Don't look at what I've done. Do it yourself. Do it now. Don't look at my notes. Don't cheat, don't cheat, don't cheat. Can you do it? So of course the first 2 columns are just copied from the top, right? True, true, false, false, true, false, true, false, right? Yes or no? And then what? Then I'm looking for P or Q. So how do I come up with P or Q? Do you remember? As soon as one of them is true, the whole statement is true. So let's make something up. Let's say that P stands for I like apples, and Q stands for I like bananas. If I say to you, I like apples or I like bananas, that statement is a true statement as soon as one of them is true. If I like apples only, it's a true statement. If I like bananas only, it's a true statement. If I like both, it's a true statement. The only time that statement is going to be false is if I don't like apples and I don't like bananas. In that case, the statement, I like apples or I like bananas would be a false statement if I didn't like apples and I didn't like bananas, right? So let me reveal that part of it so that it makes sense to you. So I'm saying that the only time this is false is when both of these are false. Every other time the or statement is a true statement. Get it? Yes? Something's up, right? Talk to me. Okay. I am taking AMS 110 or I am taking Bio 203. What are you taking? 204 this semester? What are you guys taking? 328? Better you than me, buddy. Okay. I am taking AMS 110 or I am taking Bio 203. That's my statement, okay? If I'm only taking 110 but not 203, will it be a true statement? I am taking this or that. If I'm taking this, is it a true statement? Yeah. That's why true, false is true. True or false is true, because the first one's true. As soon as one of them is true, it makes the whole statement true. Similarly, if I'm only taking the second one, Bio 203, but not 110, the statement is true. If I'm taking both of them, the statement is true. But if I'm not taking either of them, then it's false. So the only time that statement is false is if it's false and false. Then the or statement is false. Agreed? Okay, let's go to the next one. Because, of course, I'm trying to show De Morgan's law here. So the next thing I need to do is negate that, because look at De Morgan's law here. P or Q not. So I want the not of P or Q. So the not just means you go and you flip the switch on everybody. If it was true before, it's now false. If it was false before, it's now true. So I write down the negation of each of these. So the true's negation is false, and false's negation is true. So I have this whole column now. Then I need to show that this thing is equivalent to not P's intersection with not Q. So I'm going to need a not P and I'm going to need a not Q. So not P is the negation of the P column. Not Q is the negation of the Q column. Create that for yourself, right? Go negate your P and your Q. And then you want the intersection of those two things. So let's talk about intersection. I like apples and I like bananas. That statement is only going to be true if I like both. If I don't like apples, that's a false statement. If I don't like bananas, that's a false statement. So A and B is only true if A is true and B is true. Do you agree with me? So when you look at the very last column, the only time that column is true is when the previous two ones are true. That thing that's circled in the purple going horizontally. Do you see? Every other time it's false, because the and statement cannot be true if one of the statements is false. So I have showed that in every case, the two vertical purple things are equal in every single case, showing that De Morgan's law holds in every case. Follow me? What's your question? Yeah.
I did not understand the not P and not Q columns.
Okay, so ignore the not P and the just those two, those second to last and the one before. All I did was negate the P and the Q. So you see that P, let's do it. So if P is true, then not P is false. All I've done is take this column, true, true, false, false, and negate this thing. So I flipped the switch on whatever it showed in the first column. That's all. And I did the same thing for Q. What other question? So this is De Morgan's law, but the question is, how do you use it? So let's say, here's your problem, okay? See if you can do this. Probability of A is 0.5. Probability of B is 0.3. And probability of A union B is 0.6. Please find the following. Probability of not A, probability of not A and not B, probability of not A or not B, and probability of A or not B. And how about one more? Probability of A and not B. Can you do it right now, please? Oops, you can't see E. Let me move it up. Let's see if you can do it. That's a 0.6, the thing that's getting cut off. I gave you the union, right? Do you have a union formula? You should use it so that you can find the intersection and work backwards to fill in the Venn diagram. By backwards, I mean work outwards, because you cannot fill in the Venn diagram unless you have the middle portion. So go solve for the middle portion, which is A and B, and then see if you can finish up. Who's stuck? Anybody stuck? Where? Which one? A naught? What's the formula for not A? What? It's the negative of the value of A. Probability can't be negative, remember? The probability has to lie between 0 and 1. Do you mean negative? So probability of A is 0.5. So do you want to say minus 0.5? It can't be negative. Can you imagine if I said to you the probability of snow is minus 50%? You'd say, like, what are you smoking, right? Right? So what is the formula for not A? If it's not negative, like we mentioned before, then what is it? Right. 1 minus the probability of A. Where's the 1 coming from? Can I pick on you? Okay, so where's the 1 coming from?
The whole area is 100%.
Exactly. 100% is the probability of the sample space, right? So everything that's outside of A is going to be 100% minus what's inside of A. Is the middle portion part of A? That little thing that looks like that, is that part of A? Yeah. So the outside portion is just this. The outside portion to A is everything outside of this A circle. So if this is 0.5, then what lies outside is 100% minus 50%, which is also 50%. So let's get started. Not A is 1 minus the probability of A. So 1 minus 0.5 is also 0.5. Everybody okay with that? Next one. Not A and not B. I'm kind of stuck, right? I'm kind of stuck because I haven't solved for my intersection yet. So let me go do that. They told me that A union B is 0.6. So I have something called a union formula, which says probability of A union B is equal to probability of A plus probability of B minus the probability of A and B. So if this thing is 0.6, and this one is 0.5, and this one is 0.3, I can solve for A and B. Because 60% is 80% minus 20%, is it not? So this is 20%. Once I know that, I work outwards. So if all of A is 50, then this one is 50 minus 20, which is 30. And if B is 30, then this piece right here is 30 minus 20, which is 10. And then I add this and this and this. And that's my union, which they gave me to be 60%, right? So they're asking me for not A and not B, which I know lives out here. This is not A and not B, this piece outside of the union, right? So if the union is 60, then this piece is 1 minus 60, which is 40. Does that make sense? Okay, not A or not B. De Morgan. This is where De Morgan comes in. Anytime you see them ask you for something that is not one of the 4 pieces that we marked off before. Remember, like 10 minutes ago, I showed you 4 different pieces on your Venn diagram. Let me see if I can find that. If not, I'll just draw it. There are 4 pieces. There's A, not B. There's B, not A. There's not A, not B. And there's A and B. These are the 4 pieces that I know, and I don't know anything else, right? So this is something that I don't know, because they're asking me for not A or not B. The only one I know is not A and not B, which is the outside piece. So whenever I encounter something that I don't see readily on the Venn diagram, I use De Morgan. And the way to use De Morgan is the following. Pull out the negation. So this is equal to probability of something not. I'm going to factor out the negative sign. So not A becomes A. Union becomes intersection. not B becomes B. And I have factored out the minus sign. After you do this, the next step is always to say probability of junk not is 1 minus probability of junk. Meaning probability of blah, 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 blah not is 1 minus the probability of blah, 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 blah. And the blah, blah, blah is always going to sit in your Venn diagram. So this is equal to 1 minus the probability of A and B. Do you know A and B? Yes, it's 0.2. Therefore, 1 minus 0.2 is 0.8. That is the probability of everything except for him. We're saying that not A or not B is everything except for the intersection. Follow me? That's how you use De Morgan. Anytime you see something that's not one of these 4 areas here, you are going to pull De Morgan out of your hat and use it. Let's do this. It's also De Morgan, because guess what? I know A and not B, but I don't know A or not B. So again, De Morgan. Pull out that negation sign like this and switch everybody. A becomes not A. Or becomes and. Not B becomes B. The next thing to do is just 1 minus the probability of not A and B. B and not A. Do you know what B and not A is? Here's B and not A. 0.1. 1 minus 0.1 is 0.9. Finished. A and not B is just 0.3. That's this piece. That's that piece. A and not B. I'm done.